So, welcome. This is the first of our Year 9 Triple Science Remote Learning. The first thing I wanted to talk about was the schedule. I know you've probably heard this in an assembly, but just to go through it again. For Science in Year 9, on Monday there is a webinar, so that's what you're in right now, what you're watching after. We would then, we're not expecting you to do anything during this time here, during the webinar. What we would ask you to do is on Wednesday and Thursday times, 2:05 and 10:05 to 10:50, go to your Google Classroom, and in there will be a copy of the presentation as well as some Google slides and maybe some other things as well. During this webinar, I'll point out some extension activities that you might want to do. Again, that's some time where if you've done all the other things, if you want to go back and do some of those activities, that would be a good thing for you to do. I want to highlight as well the Van Dien Science YouTube channel. So as well as being in a recorded webinar folder, which this will be, this will also go on the Science YouTube channel, hopefully shortly after we've finished recording the webinar. So that if you miss it for whatever reason, maybe you can't get onto your particular devices at the particular time, you can still catch up on the webinar another time. What we're going to do is we're going to go back and have a look at some of the early stuff in chemistry. We're going back to the beginning of chemistry. So the first one is just a revision. We're going to go through basically all of the chemistry that you've done so far. There may be one or two things which maybe your class didn't get to, but the idea is we're going to go back and look at atomic structure and the periodic table and try and recap all of that in a short webinar. So the first idea, atoms are very small. Here is a rough picture. You can see here is a human, if measured in meters. If you take 1,000th of a meter, that's a millimeter. If you take 1,000th of a millimeter, that's a micrometer. If you take 1,000th of a micrometer, that's a nanometer. 1,000th of a nanometer, picometer, and 1,000th of a meter. Atoms are roughly half a nanometer across. See, so we're down in the range of nanometers, as we'll see when you look at protons, measuring in femtones. So atoms are very small. Again, something you might want to do is go and have an explore of the scale of the universe. I'm sure some of you will have seen this in class before. I use it a lot, I know, where you can zoom in and see what things are made of and see the relative scale of things as things get smaller and smaller. And you will see here is a ring which is 1 meter across. As you go in, you will see rings for millimeters, micrometers, nanometers, and millimeters. Atoms are very small. They are made of even smaller particles, protons, neutrons, and electrons. And hopefully you're all very familiar with this structure of an atom, with a nucleus in the middle, which contains most of the mass, formed of protons and neutrons, and the electrons in shells around the outside. You need to know the mass and the charge of these particles. Protons are positively charged. They've got a charge of +1, whereas electrons are negatively charged. They've got a charge of -1. Neutrons are neutral and have a charge of 0. This is where most of the mass is, the protons and the neutrons. Now, they are really tiny. You can't weigh them in grams or kilograms because they're so small. So we've invented a new unit, the atomic unit, and we've said, let's call a proton 1 atomic unit. And a neutron has the same mass as a proton. That's 1 atomic unit as well. Whereas electrons are so much smaller. They're about 1/2000th of the mass of a proton or a neutron. So to make our lives easy, we can say that they weigh 0 or almost 0. So you can see for this atom, this is where all the mass is, and then there's a few electrons around the outside, but they really don't weigh very much. So as far as we're concerned, all mass is in the nucleus here. You need to be able to read a periodic table. Here is the way they're set out. They've got an X with a symbol like C for carbon. They've got a number up here, which is their mass number, like 12 in carbon's case. And they've got a number here, which is their atomic number, which is 6 in carbon's case. This 6 tells you there are 6 protons. The atomic number tells you the number of protons. Now, you may also be able to use it to work out how many electrons there are in an atom. But what you need to know is that that tells you the number of protons. If you're in an exam and you say that says that number gives you the number of electrons, you will not get the mark. It is the number of protons. It just so happens that in most of the cases when it's an atom, the electron number will be the same as the number of protons, but that atomic number is the number of protons. The mass number, as we just talked about, is where all the mass is here in the nucleus. So it's how much stuff is in the nucleus, how many protons and neutrons added together. So you can see here in this example, we've got 12 things, 6 of them protons, 6 of them neutrons. We've got a total mass of 12 for the atom. Something you might want to have a go at is just having a look back at your periodic tables and figuring out what are the structures, number of protons, neutrons, and electrons for each of the atoms listed here: carbon, sodium, aluminium. Another point about atoms, the nucleus is the middle with the electrons around the outside, but most of an atom is empty space. The nucleus is 10 to the minus 14 meters. So we're down in picometers, again, measuring that. Whereas the atom is probably measured in nanometers. So it's about 10,000 times bigger. To give you an idea of what that would look like, if you held a pea in the middle of a football field, that's about the right scale for the nucleus of an atom to the outside orbitals of the electrons of the atom. So most of an atom is empty space, and that's going to be important when we're looking at the history of the atom as to how we discovered that. Another thing you might want to do with some of your time is you might want to have a practice building some of these atoms. So on eChalk, we have a Varndine account. You go to echalk.co.uk. The username is echalk1 at varndine.co.uk. The password is venerable master, capital M for the master, no spaces in it. Now, our account, you can only have 8 people in it at a time, so you may find you can't get into this, but you could try a different time. You can then try building an atom, that's this link here, and so by clicking on here, you can choose different atoms, and then dragging protons and neutrons into the nucleus and electrons into the correct configuration around in the shells around them. So another thing which on Wednesday or Thursday during that lesson time that you've got scheduled, you might want to do. Talking of electrons, you need to know about the arrangement of electrons. So they're arranged in shells, or sometimes called energy levels. The first shell can fit up to 2 electrons. Once that shell has got 2 electrons in, it's full, and any further electrons get put into the second shell or the second energy level. That one can fit up to 8. Once those 8 are all filled up, then any further electrons will go into the third shell. That third shell can fit 8 again. So 2 in the first shell, 8 in the second shell, 8 in the third shell. Any further electrons are going to go out into the fourth shell. It does get more complicated after the third shell. The fourth shell, the pattern, what happens here is more complicated, and you don't need to know that for GCSE. If you want to Google about what happens, then you're very welcome to. But for GCSE, you just need to know 2 in the first shell, 8 in the second shell, 8 in the third shell. You may be asked to draw electron arrangements like these up to calcium, the 20th. So 2, 8, 8, 2, with one more electron, which I'd probably put over here. Up to calcium, you can be expected to draw those. So you need to be sure you're familiar with those. Again, this will help because again, it helps you, it shows you there's 2 in the first shell, 8 in the second shell, 8 in the third shell, and you can practice all of them up to argon in that eChalk. Here's again, one final thing is the electron configuration. So here you can see there's 2 in the first shell, 7 in the second shell. We would write that as 2.7 or 2,7. So this configuration is just a shorthand way of saying how many in the first shell, how many in the second shell, how many in the third shell. Here's calcium, that's the biggest one you'll be asked to do at GCSE. 2 in the first shell, 8 in the second shell, 8 in the third shell, 2 in the outside shell in that fourth shell. Again, you can practice doing those on these slides if you want to practice some of that. That's another task you might want to do during that lesson time on Wednesday and Thursday. So we're going to look at the history of the atom. Now, the idea of atoms actually goes back to ancient Greece, and the word atom literally means uncuttable. It's some Greek philosophers sat down and thought, well, all the stuff around us, can we keep dividing it up into smaller and smaller bits, or does it get down to a tiny thing which we can't cut up? And they thought probably it got down to tiny things that you can't cut up, indivisible bits of matter, and they called those atoms. That idea was brought back by this guy John Dalton and a few other scientists around 1803. That this is when chemistry really started to get going. They started to discover a lot of elements in the 1800s, and all sorts of chemists had all sorts of ideas. And they started off thinking, right, well, atoms, these different, they're little tiny hard balls, spheres that can't be split up, and they come in different flavors. You know, we can find gold ones and iron ones and hydrogen ones. They knew a few of the elements. Over the 1800s, they discovered a whole load more, and eventually we got to the periodic table. More about that in a minute. The first thing that happened is that we discovered electricity, and we figured out that it was electrons that were coming off the atoms and moving around, and that's what electricity was. So hang on, our atoms have got things that can come out of them. The things that come out of them are negative. The electrons we know are negative. They figured that out pretty quickly. And so what was left afterwards was positive, because the atom itself is neutral. So the first step in the development of the atom was we went, there are electrons that have to be able to come out. And we created this thing called a plum pudding model. More about that in a second. That then got refined by Ernst Rutherford into this nuclear model, this idea of the nucleus. And we'll talk about that in more detail in a second as well, because this is something that they love asking about, is the transition from the plum pudding model to the nuclear model. So this is the short history. There's a few more steps in it, but I wanted to start here. And we'll dig into the plum pudding model and the experiment that led to the nuclear model in just a second. So this is roughly what a plum pudding is. It's a kind of cake which is broadly spongy with some currants in. So here's kind of a zoomed in version in a ball shape, which someone's made to represent that kind of atom. So the idea here is that you've got these currents are the equivalent of the electrons. They're the negatively charged particles, which you could reach in and pick a current out and take it out. That was the idea. But what you've got is a big ball of sponge, which is the positiveness. So they didn't really know what this big ball of positive sponge was, but they said, well, when you take the electrons out, what's left is positive. The electrons are small compared to the atom. So there's these small bits which can come out. And that's the idea of a plum pudding model. Now, there was an experiment that was done by Ernst Rutherford, where they took some alpha particles. Now, we'll learn more about alpha particles in physics. But the key thing you need to know about alpha particles is they are positively charged. So you've got these fast-moving, positively charged things being fired at a thin piece of gold. So here are the gold atoms. And what they expected was that most of them would pass straight through, and they did. What they didn't expect as much is that some of them got scattered. They got deflected off to the side, and they went, whoa, that's a bit strange. What's going on there? And what they really didn't expect is that a very small number of them, about 1 in 10,000, got bounced backwards. Well, how do you get a positive thing to go backwards? There must have been a small positively charged thing right in the middle of this atom. So they're using this to look inside atoms and to see, how do we know that there's a positively charged nucleus and it's small and only takes up the size of a pea in a football field? Well, only 1 in 10,000 got bounced back. That means it must have been small, because most of them went through or got deflected a little bit. The fact is, it must be positive, because the only way you get a positive thing to go backwards is to get another positive thing to repel it. If you had a negatively charged thing there, that would attract it. That might get it to deflect. If it came in along here and got pulled towards it and deflected, you might get some deflection happening, but you don't get any that are being turned back. Repulsion only happens with positive on positive. So the conclusion they came to is the fact that some of these, a very small number of these got reflected, but got deflected back. There's a small positively charged bit in the middle of the atom. Nearly all of them went straight through. So that led them to believe, okay, well now nearly all of the atom is empty space, because nearly all of them went straight through. So you can see how we're getting closer to the idea that we've got today of this small positive nucleus with a whole load of space around it and the electrons. Well, we knew we had electrons, so we came to this kind of a model between the positive with the electrons around it and the plum pudding. Now, a really common exam question is to compare these two models. Now, the trick with compare questions is not just to say what's different. That's what everybody finds really easy, to say the differences, but to say what are the similarities. So some of the similarities here, they're both containing negatively charged electrons. They've both got a positive element, but the difference is here the positive element is concentrated in the nucleus, which is very small, whereas here the positive part of the atom is taking up most of the space of the atom. So just be aware of those compare style questions. This is slightly misleading. We didn't quite get to this stage yet with the electron shells. This is a better picture of Rutherford's atom, that we've got a nucleus with the electrons around it and a lot of empty space. And these kind of orbiting around, a bit like planets orbiting around a sun. It wasn't until Niels Bohr in 1913 found that electrons have specific levels that they can exist at. It's almost like these shells that we now know. So I showed you a lot of scientists' names previously about Dalton and Rutherford. Actually, for your GCSE, you don't need to know those names, but the names on this slide, these are the two you do need to know specifically. Niels Bohr came up with this idea of electron shells, which we now still use. And James Chadwick, eventually we discovered, so you can see in Bohr's atom, we've just got a solid nucleus here, whereas what we now, the current model we're using, you can see here we've got protons and neutrons in the nucleus. Now, that was something which took time to develop. First, we discovered protons, and a number of different people all kind of came to that in different ways, but around about the same time. Whereas James Chadwick led up a team which was the only team who proposed the existence of the neutron. So one of the things that got us from here to here, we had to discover protons. They were discovered first, and then later a team led by Chadwick discovered the neutrons. So these two names, Niels Bohr and James Chadwick, those are two names that you must know in order to get marks in the exam. That leads us on now to the idea of relative abundance. Now, I'm going pretty quickly through this because hopefully a lot of this is revision for you. If you need to, go back and watch the videos again later to go through the things I've just said, or there will also be links to other videos explaining these same ideas. So the first idea here is that you can get different isotopes. Here are 3 isotopes of lithium. An isotope is an atom which has got the same number of protons, 3 protons, 3 protons, 3 protons, the same number of electrons, 3 electrons, 3 electrons, 3 electrons, but a different number of neutrons. This one has 3 neutrons, this one has 4, this one has 5 neutrons. And you can see that in the mass number here. There are 6 things in the nucleus. So that's lithium 6. It's got a mass of 6, this atom. This is lithium 7. There are 7 things in the nucleus. It's got a mass of 7. 8 things in the nucleus. Lithium has got a mass of 8. These are isotopes of each other, and they're naturally occurring. Sometimes you'll find some lithium atoms. A typical lithium atom is lithium 7, but sometimes you'll find some that have got a mass of 6 because they've got 1 fewer neutron, or a mass of 8 because they've got 1 more neutron. These isotopes, sometimes you get more than one which is a common isotope, and a great example of that is chlorine. Chlorine has 2 common isotopes, chlorine 35, which has got 18 neutrons to add onto its 17 protons, and chlorine 37, which has got 20 neutrons to add onto its 17 protons, so it has a mass of 37. If you go out into the world and find some chlorine atoms, about 3/4, 75% of them have got a mass of 35, and 1/4 have got a mass of 37. Now, what that means is, if you were to get a group of chlorine atoms, 3 out of 4 of them would have a mass of 35, and 1 out of 4 would have a mass of 37. But that's not very useful for us when we're trying to do calculations, which we'll get onto later in the term, about atoms and how many atoms there are, and masses of atoms, things like that. So what we need to do is work out what is the average mass. So you can see here I've got 4 chlorines, 2 35s, 3 35s and a 37. That's the same as if I had 4 chlorines which all had a mass of 35.5. Those have got the same mass. Now we know that we get more of the 35s than of the 37s. So what we need to do is we need to do a calculation to work out on average how much does a chlorine atom weigh. The way we do that is we look at the mass and the percentage. So we know that 75% is chlorine 35, 25% is chlorine 37. To work out the average, you multiply the mass and the abundance and add them together. So 75% of them are 35. So what's 75% of 35 is 26.25. 25% of them are 37s. So what's 25% of 37? 9.25. Add those together, and that's where we get to this figure of 35.5. That explains why some of the elements in the periodic table don't have an integer mass number. So chlorine has got a mass number of 35.5 on the periodic table. Copper, I think, is another one which has a mass of 63.5. The reason is there is more than one stable isotope, and what we're looking at is an average weight. Now, if you were to go and Google an A-level periodic table, you'll notice that very few of the elements actually have integer mass numbers. A lot of them have multiple isotopes, and they're, rather than having a mass of 40, maybe it's got a mass on the periodic table of 40.02. That one clearly is very close to 40, but there are a few isotopes out there, but clearly 40 would be the most common isotope in that example. For GCSE, nearly all of them have integer mass numbers, but a few of them, like chlorine and copper, don't. So just be aware of that. You do need to be able to do these calculations. So there are some questions here, which we're not going to do now, but you can have a go at, again, during the classwork. If that's something you want to practice, that's an area you need to work on. There are some questions here as part of the slides that you can work on with answers at the end. Okay, moving on to forming ions. So we talked about electrons.
Sorry, I've been asked, can you put up the equation so they can write it down? So there is an equation somewhere. I think they very quickly wanted to make a note of it. Thank you.
I would say I'll leave it up there just for a little bit, but that kind of thing, these webinars are going to be available. Part of the Google Classroom. They'll work on Wednesdays and Thursdays. The idea is you can go back, and if you want to make notes and do that kind of thing, that is the right time to do it. So this is being recorded. This will be available for you to watch again. So I'm not going to spend a lot of time. The idea is not for you to be writing down and making notes right now. You can be doing that. If you miss something, it's not like a lesson. There's not going to be the time for you to stop and make notes. We're going to just carry on, and this, like I said, this will be available, and during those Wednesday and Thursday classroom times, that's when you might want to go back and add to those notes if there's something that you've missed. Okay, so going back to thinking about electron structure, so hopefully you're familiar, or you're going to go and practice arranging electrons in this 2, 8, 8, 2 in the first shell, 8 in the second shell, 8 in the third shell. Well, this is a really fundamental idea in chemistry. All of chemistry is predicated, it's based on this first idea about electrons. And the big idea is all atoms are trying to get a full outer shell. Now, there's two simple ways you can do that. If you're a sodium atom, you've got 2 in your first shell, 8 in your second shell, and 1 in your outside shell, that third shell. So the outside shell is whichever shell is on the outside. For some atoms, that will be the first shell. For some, it'll be the second. For some, it'll be the third. You've got to look at the individual atoms, figure out which is their outside shell. But it's just the one that is furthest from the nucleus that has electrons in. There is a fourth shell on this, but it's just got no electrons in. But electrons can go there. There just doesn't have enough to fill up to that fourth shell. The easiest way for sodium to get a full outer shell is, well, instead of filling up this shell, which would take 7 electrons, it's got to find 7 electrons from somewhere. The easiest thing for it to do is to lose an electron. When that electron is lost, this shell is now empty, and this second shell becomes the outer shell. And you can see that shell is already full. So losing an electron means that the atom gets a full outer shell, which is what they're trying to do. The reason they're trying to do that is how it is most stable. Some of you may have come across the second law of thermodynamics, this idea that entropy increases, things are tending towards a more disordered state. That's, again, the law that's governing this. If you haven't heard of that, don't worry too much about it. That's more of an A-level physics concept. The key idea here, atoms are trying to become stable, and the way you become stable if you're an atom is to have a full outer shell. Let's take the example of chlorine. Chlorine's got 3 shells, and this third shell isn't full yet. It's got 7 in it. So the easiest way for chlorine to get a full outer shell is to gain an electron. Now you can see here's an electron it's got from somewhere. Maybe it's the one that this sodium lost. But this has now gained an electron, and it's got a full outer shell. It has become stable. So that's what it's trying to do. All chemical reactions are about atoms trying to get full outer shells. When they do that, if they are gaining or losing electrons, they might become an ion. An atom is neutral, and it has the same number of electrons as it does protons. That's why it's neutral. This sodium has got 11 protons in the nucleus, 11 positive charges, and 11 electrons, 11 negative charges. So with 11 positives and 11 negatives, those cancel out, and overall it has no charge. When it loses an electron, remember the electrons are negative, it now only has 10 negatives and 11 positives. So overall, there's 1 proton which doesn't have an electron to cancel out that positive charge. So it has a 1+ charge. So we would write it as an ion, Na+. See the difference here? Here's a sodium atom without a charge. Here's a sodium ion with a charge. If you see something with a charge like that, that means it is an ion. If you see it without, that means it is an atom, and it will have the same number of electrons as protons. This ties back to the beginning, one of the early things I said, saying that you can't say the atomic number is the number of electrons something has, because it may have gained or lost electrons. That's the reason that you can't say that about when you're looking at the periodic table. For chlorine here, chlorine's got 17 protons and 17 electrons. Here, it's gained an 18th negative, so we've got 17 positive protons in the nucleus and 18 negative electrons around it. We've got 1 more negative than positive, so it has a -1 charge, Cl-. These, again, so this is forming ions. Now this is we're going to use this to explain a number of patterns of behavior in the periodic table. For example, we're going to touch on this again later, group zero have full outer shells already. Helium has 2 electrons, that's a full outer shell in the first shell. Neon has 10, 2 in the first shell, 8 in the second shell, that's a full outer shell. All of these ones here in this group have full outer shells. You'll notice this is group 0 because that's kind of like its outer shell has got 0 in it. All of these group numbers tell you how many electrons they have in their outer shell. All of group 1, if we go back and have a look, all of group 1 have got 1 electron, 1 electron, 1 electron, 1 electron. They all have 1 electron in their outside shell. All of group 2, again, beryllium, magnesium, calcium, have 2 electrons in their outside shell. These ones in the middle are transition metals. We're going to talk about them a bit more later. Transition metals, you can't predict how many electrons they have in their outside shell or what kind of ions they will form. Sometimes you just have to learn them. Again, that's more of an A-level thing than a GCSE thing. But here we have group 3. Group 3 all have 3 electrons in their outside shell. If they form ions, they will all form 3+ ions. They're going to lose 3 electrons. Group 7 over here has got 7 electrons in their outside shell. If they're going to make a full outer shell, they're going to gain electrons. They're going to form a 1- ion. Group 6 here, they need to gain 2 electrons if they gain electrons to make a full outer shell. So oxygen, for example, forms a 2- ion. Nitrogen is in group 5. If it's going to get a full outer shell, it's got to gain 3 electrons. So if it's getting a full shell by gaining electrons, then it's going to form a 1, 2, 3- ion as it's gained 3 electrons. So these forming ions, to an extent, you can predict what happens by looking at what group it's in. That can tell you what kind of an ion it will form. For the transition metals, you can't predict it. They're strange, and we're going to talk about them more in a bit. But for things in group 1 and group 2, they always form 1+, 2+ ions. The metals in group 3, so aluminium, gallium, indium, and thallium, all form 3+ ions. Lead forms a 4+ ion because it's going to lose 4 electrons. Carbon doesn't form ions. Some of the group 4 will gain or lose, in lead's case, lose electrons. Carbon never forms an ion. You don't get carbon ions. You do get ions of some of these. Group 7 form ions very easily. Some of the ones in group 6 and group 5 do as well. And you should be able to predict the charge on the ion based on its position in the periodic table, with the exception of the transition metals, which you can't predict the charge of that ion. There are also these groups in the periodic table also sort of link to chemical behavior. Lithium, sodium, potassium all behave similarly. Fluorine, chlorine, bromine all behave similarly. Not identically, there are differences, but they have similarities. There are patterns in their behavior. And group 0, they all behave the same because they do not take part in chemical reactions because they already have a full outer shell. They don't need to go and get electrons or give electrons away to get a full shell. They've already got them, so they don't need to interact with other elements. So just a summary there. Atoms in groups 1, 2, and 3 lose electrons. 6 and 7 gain electrons. Group 4 share electrons. We're not going to focus much on these ones in the middle, which are sometimes weird. The GCSE really focuses on group 1, group 2, and group 7 and group 0. Those ones are the ones that come up most commonly. We talked about it's charged, gaining or losing electrons. So just to recap here, because electrons are negative, if you lose a negative, then you're going to end up with more positives than negatives. You can think about that purely mathematically and counting up how many protons there are and how many neutrons there are, or I have a kind of an emotional way of thinking about it as well. If you imagine someone who's a mixture of positive and negative emotions all the time, they've got some good things in their life, some bad things in their life. If you can get rid of a negative thing, then overall, they're going to end up more positive. They've got more positive going on than negative. So if you lose a negative emotion, you feel more positive. If you gain a negative emotion, if you're kind of in that middle ground where you're kind of okay, if you gain a negative emotion, you're going to feel more negative. So it's always electrons that are moving. Protons and neutrons never get transferred around. It's only ever electrons. They're on the outside of the atom. It's easier to get those to move around. These ones in the middle are pretty much stuck in place. So ions are only ever formed from gaining or losing electrons. If you gain an electron, you gain something negative, you become negative. If you've lost a negative, you become positive. Brings us on to thinking about the history of the periodic table. So back in the beginning of the 1800s, when chemistry really started to get going, there were two main ways people put together the elements. Now, they were discovering elements. You can see this is far from an exhaustive list, this picture here, but that is a real picture of how they went about trying to organize their thoughts about all these different elements. There were two things they knew about them. They knew how heavy they were, their atomic mass, and they knew how they behaved chemically. So some people like to make lists, and you can see here we've got hydrogen at 1, and we've got slightly heavier ones, oxygen at 7. That's wrong. Oxygen should be closer to 16, but they were making mistakes in their experiments. But they were trying to impose some sort of order to get their heads around how is the world arranged in terms of elements. So some people arranged them by mass. You can see the masses going up here. And some people thought, lithium, sodium, and potassium, they're kind of similar. They all behave similarly when you put them on water, for example. Calcium, strontium, and barium, they're kind of similar. Let's put them in a little group of 3. Chlorine, bromine, iodine, they're similar. Let's put them in a group of 3. Sulfur, selenium, tellurium, they're similar. Let's put them in a group of 3. And this idea of triads. So some people were organizing them by their mass. Some people were organizing them by their property. There were people who tried to do both, and John Newlands came up with this idea of octaves. And he said, well, look, if you arrange them in 8s, you get this repeating pattern, 1, 2, 3, 5, 6, 7, 8. Every 8th is similar to the previous one. So hydrogen is similar to fluorine. And then if we go 1, 2, 3, 4, 5, 6, 7, 8, the next 8th one again. So we've got a row of 7, and every 8th it repeats, and it's kind of got similarities. Kind of like those of you who know a bit about music, you know that you get these octaves where a low C and a high C have a similar kind of sound, although they are different notes. So he thought there was a direct link here to musical notes and called this the law of octaves. This was all groundwork, which meant that Dmitry Mendeleev in 1871 could come up with the first draft of what we now recognize to be the periodic table. And he did a couple of things which were pretty amazing that other people hadn't done, and is the reason he's sort of seen as, he's remembered as the person, rather than these other people I've mentioned. Mendeleev, again, this is one of those names you've got to know, along with Bohr and Chadwick. Mendeleev as the person who first developed the periodic table. What he did is he got a whole load of cards and he put their masses on, and then he started trying to combine a bit like Newlands had done, tried to combine their masses in order and their chemical properties. What he kind of figured out was that maybe he didn't have all of the elements. So the amazing thing he did is he left gaps. So he left this one here, which is, I think, scandium. They hadn't discovered it at the time. He left the gap there for saying, well, scandium's there's going to be something there, and I think it's going to have a mass of about 44. So he made some predictions as well. He said it's going to behave similarly to like to boron and aluminium. It's probably going to be a metal, and it's going to weigh around about this much. And here, where we've now got gallium and germanium, again, he left gaps and said, I think we're going to discover these, and they're going to behave like this. They'll have their melting point between this range and this range. They'll have a boiling point of around about that, and their masses will be about 68 and 72. He wasn't far off. That's actually 70 and 73, but he was kind of, stab in the dark. It's going to be around about that, and he got it broadly right. So he left gaps, which meant that it lined up much more nicely. He also ignored the mass number to an extent. Tellurium has actually got a mass of 128, whereas iodine has got a mass of 127. So he went, well, I'm not actually that fussed about being exactly in strict mass order. I'm happy to swap them around if it makes sense for their chemical patterns. Now, he didn't understand why that was the case until we discovered isotopes, which we looked back at that relative abundance. Sometimes you just get a more common isotope of one particular element. So the key thing here, he combined both arranging them in order of mass and in chemical properties, and left gaps and ignored the relative mass where it was inconvenient. He went, well, I'm just going to ignore that. Don't worry about it. And you can see there's quite a lot of gaps here. We've since discovered those. Now, they used to do it by mass. Now it's arranged by its atomic number, the proton number. Hydrogen has 1 proton, helium has 2, lithium has 3, beryllium has 4, boron has 5, carbon has 6. It's arranged now by the atomic number rather than the mass number. So for our modern periodic tables, there's a few examples where the mass number doesn't check out, like the tellurium iodine one. It is now arranged by the atomic number. Again, some extension, this isn't required, but some of you might be interested. There's a New Scientist article here, which talks about why maybe our periodic table needs a bit of a rethink. We should be changing how we're presenting it. So again, during that class time on Wednesday or Thursday, you might want to go and have a read of that article as an extension. Brings us on to starting to look at patterns in the periodic table. So here we've got group 1. Now in group 1, they've got 1 electron in their outside shell, and that explains why they behave similarly. They're all trying to do roughly the same thing. They're all trying to lose that 1 electron, and they do it in broadly the same way. You might have seen them react with water, where they sort of fizz around and move around, and then sort of some of them have a little explosion, but they all react vigorously with water, which is really unusual for metals. Think about most metals, if you put them in water, they don't suddenly spark and start reacting. Group 1 are all very reactive. They're all very soft metals. They all react quickly with oxygen. They oxidize. Again, you may have seen that in lessons where you can cut them and then they quickly tarnish. They go from being shiny to not being shiny. And that happens increasingly fast as you go down group 1. So again, you may have seen that this reactivity, lithium fizzes a bit, sodium scoots around quite a lot, and potassium actually sets fire to itself when you put it on water. They become more reactive as you go down. They're all going to form 1 plus ions trying to get rid of that electron. So again, they all have the same kind of reactions. They're very similar chemically. To explain why they get more reactive, though, we need to think about their electronic structure. So here's lithium with 1, its outside electron is in the 2nd shell. Here's sodium, its outside electron is in the 3rd shell, and potassium, its outside electron is in the 4th shell. That's the electron they're trying to get rid of in the 2nd shell, 3rd shell, 4th shell. So there's 2 key ideas here, and they're both kind of linked to this, they're strongly linked to this electronic structure. Lithium's trying to get rid of this negative electron, but its nucleus is positive. So we're just showing the outside shell here. So we're just showing that second shell here for lithium, the 3rd shell for sodium, and the 4th shell for potassium. This negative electron is trying to get rid of it so it can have a full outer shell, but it's got a positively charged nucleus. Now there is a force of attraction, an electrostatic force, attracting that negative thing to the positive thing. That negative electron is being attracted to this positive nucleus, and that negative electron is being attracted to this positive nucleus. The difference is how far away they are. Because lithium's only in the 2nd shell, its electron is closer to the nucleus, whereas potassium, because its electron is out in the 4th shell, is much further away from the nucleus. Now, you might have experienced this with magnets, where if you get 2 magnets close together, they'll push together, pull together hard. That attraction is a big force. But if you have the magnets further apart, the force isn't strong enough to pull them together. The further away they are, that negative is away from the positive, the smaller the force is going to be. So if you imagine this electron is being attracted really strongly to this positive nucleus, imagine that that's connected together with maybe some rope. You can break it, but it's going to be hard to pull it. This one is a bit further away. The force is a bit less strong. Instead of rope, maybe this is attached by string. Again, it's still attached, it's still being pulled in, but it's going to be easier to break that string. And this one here, is because it's even further, that force is going to be smaller, so that force is going to be being pulled in with maybe by like an elastic band or a bit of spider thread or something. So it is being pulled in, but it's much easier to break that away. It's easier to lose that electron, so it becomes more reactive. And if you go even further down, the electron shells get further and further out in the 5th shell, the 6th shell, the 7th shell, and it becomes easier and easier and easier to lose that electron because that electrostatic force between the positive and the negative gets smaller and smaller. So that's the first idea, the electron itself being lost and how strongly it's being attracted to the nucleus. The second idea is called shielding. So let's have a look at this picture over here. These are our outside electrons, and as we talked about, they're being attracted by the positive nucleus, but they've also got shells of electrons inside them. Now those are negative. When you get two negative things near each other, they're going to repel. So this electron is being pushed away by this electron and this electron because they're both negative. Have a look at potassium. See this electron here? It's going to be pushed away by these two electrons and these two electrons. So it's got four negatives pushing it away. So it's got, as well as a smaller force pushing it in, it's got a big force pushing it away. Look at sodium. Well, it's only got these two electrons. This electron is being pushed away by two electrons, not four. So it's got a stronger force pulling it in because it's closer to the positively charged nucleus, and it's got a smaller force pushing it away because there are fewer electrons in between it and the nucleus. There's fewer electrons pushing it away, shielding it. And lithium, closer to the nucleus, so it's got a stronger electrostatic force pulling it in, and it's got no electrons here pushing it away. So this idea of shielding is how many electrons does it have inside it which are having a repulsive force, a pushing away force on it. So two reasons that it gets more reactive as you go down group one. The force holding the atom together, holding this electron in, is an electrostatic force, and as you go further out, that force gets weaker. There are also more electrons as you go into these bigger and bigger atoms, which are providing electron shielding. So that explains that pattern, why if you go down group one, you get more reactive. Group 7 has a similar thing, but in the opposite direction. So you can see in group 7, what they're trying to do is they're trying to gain an electron. Here's where the electron for fluorine is going to go. Here's where the electron for chlorine is going to go. Here's where the electron for bromine is going to go. So again, you can see we've got the same pattern happening about distance from the nucleus. This gap here is close to the nucleus. This gap here is a bit further away from the nucleus. This gap here where an electron is going to go is even further away. And again, you can see the shielding. So here we've got 2 electrons shielding. Here we've got 4 electrons shielding. The difference is they're trying to attract an electron. So this one will find it easiest to attract an electron. The attractive force is biggest because it's closest to the nucleus, and the repulsive force is smallest because it's got the lowest amount of shielding. Whereas in bromine, we're further away from the nucleus, so there's a smaller attractive force, and we've got more electrons shielding, so there's a larger repulsive force. So fluorine is going to find it much easier to attract that electron into that gap than bromine will. Bromine's going to find it harder because it's got a smaller attractive force and a bigger repulsive force. So what that means is that they get more, as you go down group 7, they get less reactive, or as you go up, they get more reactive. Why is that? The electron being gained is closer to the positive nucleus, so you're going to get a stronger electrostatic force in fluorine than you are in bromine. There are also fewer other electrons to provide shielding, that repulsive force that pushes it away. So there's bigger forces pulling in the electron to fluorine than there is to bromine, which is why it reacts more readily with fluorine than with bromine. Something you need to be aware of in both of these is you can demonstrate this reactivity in both group 1 and group 7 through displacement reactions. So if A is more reactive than B, so let's say this is potassium and this is lithium, then the potassium can kick the lithium out and take its place in a compound with something else. Let's say this is chlorine. So here we've got some lithium chloride reacting with potassium. Potassium will take the place, displace the lithium in the compound and form a pure element of the lithium. That works in group 7 as well. Imagine that this is our metal. Imagine this is the potassium, and here we've got some bromine and some fluorine. So we've got potassium bromide reacting with fluorine. Because the fluorine is more reactive than the bromine, it will kick out the bromine and take its place in the compound to make potassium fluoride and bromine. And you can demonstrate that in a classroom by reacting these together. Here you can see we've got chlorine and potassium bromide. Now, chlorine solution is kind of this clear liquid you can see here. This slightly yellowy liquid means it's got bromine in. So after it's reacted, the bromine has been kicked out into the water, and we've got the potassium chloride dissolved here. You see all of these dark colors. This shows that the iodine, which was present in the potassium iodide, has been kicked out by the chlorine. It's been displaced. So you've now got potassium chloride in here and iodine, which has been dissolved into the water. So you can do these displacement reactions to show which one is more reactive than which. The one that is less reactive is going to be displaced and become an element rather than taking part and being part of the compound. We've touched on group 0, but again, there's patterns in group 0. We know that they are all very unreactive. The reason they are unreactive, they are inert, is because they already have full outer shells. They are not trying to gain or lose electrons. They've already got all the ones they need to be in that most stable arrangement. Another thing you need to know about them, though, is the patterns of what happens. You can see as you go down, helium, neon, argon, krypton, you can see there is a pattern here in melting points and boiling points. You get this same pattern actually in group 7 as well. Now, this isn't a super complex point, but just be aware that there are patterns that go on here, and you may be presented these in sort of a graph form or a table form and asked to make a prediction maybe, or to describe the pattern. So as we're going down here, we're getting increasing melting points. Even though that number is getting smaller, remember this is a negative number. Minus 157 is a bigger number than minus 272. So this is increasing, even though the numerals look like they're getting smaller, because this is a negative number. And again, you can see there's a pattern here in density. As we're going down, we're getting more dense. That's not surprising because we're getting heavier and heavier elements. So that completely makes sense. Going back for a second here, so remember this block in the middle were the transition metals. And I said we were going to look at the transition metals in a little bit more detail. Well, we're going to look at them now. They are all metals, hence the name transition metals, and they're in this transition between group 2 and group 3, which is where they get their name from. There's two main things which you need to know about transition metals. The first is that they are unusual in that they form colored compounds. Most other chemicals, when they form a compound, either make a white powder maybe, or a clear liquid when they're dissolved. Transition metals give you amazing colored compounds, things like copper sulfate. I'm sure you've seen before that amazing blue color. Maybe you've used potassium permanganate, which has got manganese in and makes this amazing sort of purpley pinky colored, which you may have seen to show diffusion or convection currents when dissolved in water. So all of these transition metals form colored compounds. The other thing, here they are as metals, but when you get them in, so that's as a pure element, but when they get into compound form, they're often colored. And that's what gives a lot of the colors in gemstones or precious stones or minerals. So if you've seen something like malachite, which is an amazing green colored stone, the reason it's green is it has a lot of copper in it, and those copper compounds are what give it its green color. Things like rubies. Rubies are red because they have vanadium in them. And that vanadium is what gives them that red color. So those colored compounds come up a lot in geology, and cool looking rocks probably have transition metals in them. Here they are. All of these ones here, you can see here's their melting point. You can see they've all got relatively high melting points. So not as high as carbon, but these here are the transition metals. If we compare it with some of the group 1 metals, look, here's lithium, here's sodium, here's potassium. They have much lower melting points. Transition metals, this big block here from scandium onwards, this is our transition metals, until we get over to gallium. So from scandium to zinc, they've all got very high melting points. Again, another thing which contrasts them with the group 1 metals. They're all much harder. You may have seen people being able to cut group 1 metals. Transition metals tend to be a lot stronger. Think about copper is one you've probably got a lot of experience with, or silver, or maybe even if you're lucky, some gold. But they're much harder metals compared to those softer group 1 metals. Again, this area on transition metals is one of the triple only bits of the content. So this isn't something which you would be doing if you were doing combined science, just doing the double science. So right at the end of this, I've got some questions with answers to help you have a look at some of those transition metals. Again, something that you might consider doing on that Wednesday or Thursday, as well as the Google form, which is going to go up into your Google Classroom, and maybe some of those activities that I've highlighted throughout this. There's the odd questions, there's a few extension activities, there's a few which are maybe more, well, I want to just make sure I'm solid on the atomic structure. I'm going to go and build some atoms. It's going to be up to you to choose those. The one thing that we are going to ask that you do is that you do the Google form. Maybe you want to have a go at practicing building some atoms for yourself, that's fine. But the Google form is the one thing you must do. All of the other things are optional, and you can choose to fill your time how you want. One final thing I want to say is you've got 2 slots which are on Wednesday and Thursday. They're only 45 minutes each. You shouldn't be doing more than an hour and a half of science outside of the webinar. So if you found that you're doing the task we're setting you and it's taken you 3 hours, you've done too much. An hour and a half. Try and limit yourself. 45 minutes on Wednesday, 45 minutes on Thursday. If you want to do a little bit more than that, that's fine. But just be aware of the balance of all of the other competing subjects you've got. Make sure you're not spending too long. You should be working a normal school day. So if you find that it's got to 6 o'clock and you still haven't finished all your schoolwork, then just let your teacher know. Submit what you have done. Send them an email explaining what you've done. Say, I didn't finish all of it, but I've got up to this point and I spent this amount of time doing it. That'll be good feedback for us. If we're setting you too much work, then that's a problem and we need to look at that. So please do tell your teachers where you got to when you've been doing these works. Now, speaking of which, we've got 3 minutes left. Just if there's any burning questions, Miss Wonstel, if you want to pipe up and share them. But otherwise, I'll just leave it a couple of minutes for you. If you've got any, put them in chat now. Miss Wonstel will then ask them to me.
I'm just waiting to see, sir.
Wonderful.
I think you've answered most of them. I had someone say that the homework was really hard, and that would be on me. I make the Google form homeworks, and I do make them really, really difficult on purpose. So do not stress it if you find them difficult. The whole point is they were meant to be.
Hopefully, though, you've seen there are some other activities which are designed to be a bit easier or a bit more engaging. So we tried to mix it up and not just had you just doing Google Forms. There's some reading there. There's some activities for you to do. There are also some practice questions which you can practice on this this presentation, which will go into your Google Classroom. Sorry, Miss Wonstel, you dropped out there. Do you want to try again?
The Google form that I am making at the moment is nice and easy and multiple choice, so shouldn't be a problem. And in terms of Google form, I believe do it on Thursday would be the best looking at, or Wednesday, but later in the week.
Yep. So even though they may be in your classroom, that's the times that you should be doing them is Wednesday and Thursday. Try and stick to your timetable. Okay. Anything else popped up, Miss?
No, just been answering them.
Okay, wonderful. So have a look in your Google Classroom. If you have any questions or any problems, do email your teacher. And I hope you have a great week.
Just going to clarify, you do not have to do anything more today. This is science done for the day.
Yep.
I believe the subjects afterwards, but that will be on your remote learning timetable.